So welcome to the first chapter in Unit 6, Chapter 23, and then you'll see in subsequent chapters we are still talking about hypothesis testing and confidence intervals, but now we're going to be talking about means. And we touched upon the difference between proportions and means earlier in Chapter 18 and then in Chapter 19, and then haven't really talked about it. The rest of the focus for Unit 5 was all on proportions, but now we're going to start talking about means. Okay. So we've created confidence intervals and tested hypothesis about proportions with one group and with two groups, and now we want to do the same thing for means. Okay, just as we did before, we base both our confidence interval and our hypothesis test on the sampling distribution model, and that was the experiment that we did with the Hershey's Kisses and tossing them up in the air and which way they would land. Okay. And then we talked about the central limit theorem, and we said that as long as the sample gets larger and larger and larger, we can say that it becomes a normal model and looks more like that sampling distribution is a normal model. And the mean of the sample is mu, and the standard deviation is this formula right here. Okay. So you're going to want to write this in your notes again. If you don't do it now, it will come up again and again. So we'll look at this, okay? So the standard deviation of that sample is going to be the standard deviation over the square root of n, and n is the number of people in your sample, okay? So in order to be able to use the formula, we need a random sample of quantitative data. Okay, that's easy enough to do. And we need the true population standard deviation, because when we're talking means, it's a little bit different than with proportions, and we don't know what that standard deviation is. It's really difficult to get the standard deviation of the true population because we don't even know when we will have the true population. We don't know when we'll have every single person sampled. It's unrealistic to think that that can actually happen. So we have a different way of referring to this, okay? Proportions, just to remind you, proportions have a link between the proportion and the standard deviation to with the sample proportion. Okay, but it's not the case with means. It doesn't happen that way. So knowing the sample mean doesn't tell us anything about the standard deviation. We need to have a very large sample in order to be able to do that, and that's just not going to happen. So we want to estimate the population parameter, which is this symbol right here, with the sample statistic. Remember that population and parameter, that's everybody, and the sample statistic is the small group that we're going to say is representative of the entire sample. So our standard error is right here. And last chapter, we talked more about the difference between the standard error and the standard deviation. So first of all, our standard error is going to be the sample statistic, the sample standard deviation over the square root of n. Okay, so now we have more variation than we did originally. Okay, and we have to allow for that extra variation, and we don't want to mess up the margin of error too much. If we have a very small sample, that sample statistic is going to be very much off from what the population standard deviation is. Okay, the shape of the model is also going to change, and it's not going to be normal anymore. Okay, so what do we do with the sampling model? Because remember, we said we need a very large sample in order to have it look more normal. So the smaller the group is, if we're talking about means, then it's not going to look normal. Okay, so a mathematician, long time ago, developed a way to approximate what our normal model is going to look like when we have means. So keep in mind that what we're talking about now is a mean as opposed to a proportion. Most of the time when we're pulling data, it's going to be means that we're testing, not the categorical data of the proportion. Most of the time it's going to be means that we're interested in. So what we're learning now is more likely when those of you who are going to take more research study classes and more statistics, this is more where it's going to lie. Okay, so this man, Gossett, William Gossett, he created a sampling model. Okay, so it's called the student's T, and you'll see it as a t-test, a t-value. Okay, it ends up forming a whole family of distributions, and the new word here they're called degrees of freedom, and the degrees of freedom are going to depend on the parameter, which is what that says here, and it's going to depend on how big your sample is. Okay, so the degrees of freedom is related to the sample size. And usually you see it like this. You'll see what's going to happen in a little bit. So T and then subscript DF, because we know that when we're using a T model or a T test, we have to use degrees of freedom. Okay, so first of all, let's talk about what our confidence interval is going to look like. Okay, so when the conditions are met, and we'll talk about the conditions a little bit later, a few slides later. So when the conditions are met, this is what is going to be the standardized sample mean. Okay, so we have our difference in the mu's, or the mean for the sample and the mean for the population. And then we have what our standard error is. Okay, and this will come up, I'm going to get back to that, but n-1 degrees of freedom is what we're going to use in order to help us find what our t value is. Okay, or our t asterisk, you'll see that. All right, and then we estimate this standard error when we're talking about confidence intervals. Okay. All right, so when he corrected the model, it didn't actually, it adjusted it. The margin of error got larger, so that's why we have these degrees of freedom in there. Know too that your confidence interval is going to be just a little bit wider, and your p-values are just a little bit larger than they were with the normal model. But by using the T model, we've actually compensated for that, and they've done enough testing where we know that this is very close to what it actually would be. So there's that little bit of a gray area in statistics again. So once the conditions are met, we're ready to find the confidence interval for the population mean. Okay, so here is my confidence interval. So the y bar, which is my mean for the sample, plus or minus the t asterisk and t minus 1. Okay, and this is going to come from a table, and I have one that you're going to keep in with your notes. So I have a table that you're going to look at, and then that is times the standard error, multiplied by the standard error of y bar. Okay, so the critical value depends on the particular, this critical value, this value right here, is going to depend on the confidence level that you specify, and then the number of degrees of freedom. Okay, we get this n-1 from the sample size. Okay, so two things you have to know in order to use the chart to figure out what this t, the critical value is with means. Okay, we have to know the c, or the confidence level, and we also have to know how many people are in your sample. Okay. Okay, so the students' T models are going to be, and remember the students' T models are not you students, that's what this Gossett plan looks like. Okay. They are going to be normal, they're going to be unimodal, symmetric, and bell-shaped, so they are going to be that normal curve that we've been used to, but with a few degrees of freedom, which means you have a very small sample size, you have fatter tails. You have fatter tails than normal. So that's what makes the margin of error bigger. And you'll see when we look at the chart that has all the t values on it, that depending on the degrees of freedom, you have a larger margin of error. So you'll see that when you look at the form. Okay, so here's a good example as well that shows you the difference. Okay, so here is our normal model in this blue dashed line. And the T model with the 2 degrees of freedom, it is a little bit shorter, it's a little bit narrower. These tails are fatter, that's what they mean, that they're a bit taller than with the normal model. Okay, so as the degrees of freedom increase, the T models look more and more like the normal model. Okay, so that it's good to have a larger sample size. So when they're talking about infinite degrees of freedom, they're saying that the larger the sample size, the closer to normal it is, which is what the central limit theorem was telling us way back in chapter 18. So here are the assumptions and conditions, and most of them are identical to the ones we've already done. Okay, so we just have to make these assumptions just like we've done with the confidence intervals and the hypothesis testing, whether we had one sample proportion or two samples. Okay, so here are the assumptions. You're going to see they look exactly the same. So I'm going to go through these pretty quickly. The independence assumption, okay, the data values should be independent, that it was collected randomized. The 10% condition, those are all exactly the same. Okay. Now, here's the only one that is different, okay? We have to assume that, well, we don't know if the data came from a population that follows a normal model, but we can check a nearly normal condition. And that means that you are going to be making a histogram. And you can put the data in your calculator and be able to see what the histogram is. We're not going to be doing a normal probability plot. Okay, so you'll put the data in, and we'll go over that in class, make the histogram, and show that it is going to be unimodal and symmetric. It can be skewed a bit in one direction. That's okay. It just can't have lots of outliers. Okay. All right. The other thing is, and this goes with that nearly normal condition, and it depends on the size of the sample. So if the smaller the sample size, the more closely it should look like a normal model, because we won't be able to use enough degrees of freedom to get it to look closer to a normal model. And when sample sizes are between 15 and 40, then the t works well. So as long as they are unimodal and reasonably symmetric, we'll be fine. And then for larger sample sizes, then the T methods, this process will work just fine. So yes, you should make a list of what these three things are and stop the video if you need to, if you haven't written them down yet. So here's the chart that we're going to use. This is only part of the table, and I will give one of these to you so you have it with your notes. Okay, it depends on the degrees of freedom, and the degrees of freedom it's one less than the sample size. So when you see degrees of freedom, n minus 1, for now, that might change with other tests that we're doing, but for now the degrees of freedom are n minus 1, and n, remember, is your sample. Okay, so n is the sample. Okay, and what you do is, and the chart that I'm going to give you, it looks a little bit different, but here we have our two-tail or one-tail probability, and here is, let's look at a one-tail probability with 10% alpha level, or what our C value is. And as you look down here, if you only have 1 degree of freedom, you only have 2 people in your sample, then that T value is 3. And as we go all the way down here, we see that they get much, much closer together because we have more people in our sample. We're not talking thousands of people in our sample aren't necessary. Okay, but you can see, and we'll talk more about how to read this chart. So the same comments hold true with confidence intervals. These are all the things not to say. All right, and you guys were very good about making sure that you said the correct using the correct words in order to figure out where the true mean is. So these are all what not to say. I'm just going to scroll through these. If you need to pause the video to read them, you can. This is exactly what you would say, what you should say. And the one I'm putting the box around here right now goes exactly with what we've said in with proportions. I'm 90% confident that the true mean is between 29.5 and 32.5 miles per hour. The key words are, where is the true mean, and your level of confidence. Okay, making a picture is always very helpful. Excuse me. When you draw the normal model and be able to see where the p-value is and where the alpha level is, it becomes more clear. Okay. So the only way to do this is you're making a histogram, and that's what you're going to have to do in order to see if we can proceed with the t-test. Okay. All right, so now we move on to hypothesis testing. So all of that was for confidence level, and now we're going to look at the t-test, one sample t-test for the mean. Okay, so you still do the same thing with the conditions. Okay, you test the hypothesis so that the mu of the sample, or the mean of the sample, is equal to the mean of the overall value that we're checking it against. And here is your formula. It looks very familiar to what we've done in the past. Okay, and the standard error of the sample, we've talked about that as well. Okay, and we're going to use this model to come up with what the p-value is. So all of it, it's different formulas. Okay, so there's a couple of little differences with this because it's a t value instead of the z, and you have to figure out how to use this chart and a couple of different formulas, but you'll have a printout with all of those on there as well, and make sure you're just clear about putting those in your notes. Okay, so significance and importance, starting to use those words, statistically significant. It means that we have enough data that says that we're fairly confident that the data says to do whatever. Okay, always a good idea to when we test the hypothesis to check the confidence interval and make sure that the value is between there. Okay, we had a couple of worksheets where you were doing hypothesis testing and also the confidence interval to help you decide should you reject or fail to reject the null hypothesis. Okay, so confidence intervals and hypothesis tests are really the same. I've drawn this picture on here as well. Let's say we have a 95% confidence. Okay, so here's my 95% confidence interval. This is where my hypothesis testing is. Okay, so this would be a two-tailed test with alpha levels of 0.05. This whole normal model needs to add up to 1. So again, the confidence interval contains all the null hypothesis values, and we can't reject those. We can't reject with that data. So if this is your confidence level between here and here, and your null hypothesis is in between those values, then we're fairly confident that the true, whether it's a proportion or mean, is going to lie within there. So we don't have enough evidence to be able to reject and land in one of these ends. Okay. So level C confidence interval contains all of the plausible null hypothesis values that would not be rejected by a two-sided hypothesis test. That's what I just said on the previous slide, so if you need to rewind this and listen to how I put it again, please go ahead and do that. Okay, and here is another piece of information. When the hypothesis is only one-sided, then the corresponding alpha level is 1 minus what that confidence level is divided by 2, because we're only in one side. We don't have both of the ends of the tails added together. Okay, so that's what we're looking at when we're talking about a confidence interval. We're talking about this, okay, or right here. Okay. All right, so sample size. This also came up in class. You're going to see that a lot of this is very similar. And remember, you're finding the sample size based on the initial information that you had. You don't know what the sample is yet. You don't know what that sample mean is yet. So we're not going to use the error in here as we did with the confidence interval. Okay. So here are a couple things we don't know. So we don't know what S is because we said we were figuring this out a bit differently. We don't know what that is. Well, in order to find what the sample size is, we have to make a guess. Okay, and we would make a guess from using a small pilot study. And a pilot study is a sample that we would collect, but they are similar to the people we're going to actually use in our study, but they're from a different place. So we can't actually use them as part of our survey. So let's say we were giving a survey to 12th graders at LPS Hayward. Well, maybe what we would do is we would actually survey seniors at LPS Richmond, and then use that standard deviation when we're going to survey our own students here. That's one way to do it. Okay. If you have to, you can use the Z critical value in place of the T value, And that works. They're close enough. And remember, we're just kind of approximating what our sample size is. We're not actually going to use those numbers. We're just getting an idea. Okay, so sample size is never exact. It depends on quantities you don't have until you actually collect the data. But it's always good before you collect data to say, well, this is roughly what my sample size is going to be. Okay. Okay, so here is a formula to be able to find the sample standard deviation. It's similar to what we've done before. Okay. And if you notice in the calculator, you actually come up with two standard deviations. You have one for the sample and one for the population. And this is what the calculator is using. Okay, so it's still the sum of the differences in each value minus the mean. That quantity is squared. Remember, the sum is that you're adding them all together divided by how many people are in the sample. And that's how we'll get our sample mean. Now, to make it a little bit closer, okay, is if we divide our denominator by n minus 1, those degrees of freedom, we actually get a better standard deviation for the population. We actually come up with a better value by doing that. So you'll see the n minus 1 when you're finding the standard deviation for the sample. That's how the calculator figures that out. Okay. All right. So some things that can go wrong. So making sure that when you're using the conditions that you're not going to be using, you need to make sure that you don't have multimodality. So you don't have lots of modes with your data. That's why you're using the histogram. You don't want the data that's too skewed. Try re-expressing. You will not have to be doing any of that. We'll re-express data as part of our review for the AP test. And you want to make sure to be aware of outliers. These all are just the same. Watching out for bias, making sure your data are independent, making sure that they're randomized, okay? Making sure that you're using the correct language for your confidence interval. All right, and I think this is the most important. The next two slides are the most important one. This is really everything is the same for means as it was on proportions. We do the same thing. Just the mechanics and the model is what have changed. Those are what have changed. Okay. So what we say about a population mean is inferred from the data. The T family is you're going to use degrees of freedom. These are the things that are different. Ruler for measuring variability is the standard error. And finding the margin of error is based on that ruler and the T model. Okay. So the reasoning of inference, the need to verify that the appropriate assumptions are met, and the proper interpretation of the confidence intervals for the p-values, that's exactly the same whether it's means or proportions. Okay. So that is the end of the information for Chapter 23. Make sure you have those formulas written down, and we'll go through plenty of examples over the next few days. Okay, that's it. If you want more information, you can go back and you can read the book, read the chapter, and gain another perspective on this information. Okay?